Afternoon, everyone.
Does that make you love me, baby? Does that make you love me, baby? Does that make you love me, baby?
So, how are we doing? Questions before we begin? Today we'll just do things with annuities, present value, accumulated value, that kind of thing. We're not going to introduce any new material, just going to revisit those ideas, apply them, and that's it. That will finish up chapter 5, is it? On interest. Yeah, chapter 5, exactly. And so after the break, we can start a completely new topic, namely probability. So just so we're clear, right, we saw two ideas, namely the present value, of $1 payments made at regular intervals for n consecutive periods at rate I per period. We denoted that by A and I, and we saw that that was 1 minus 1 over 1 plus I to the n over I. We also saw the accumulated value or future value S and I. Again, future value of $1 payments made at regular intervals for n payment periods at interest rate I per period. This was 1 plus I to the n minus 1 over I. There you have it. We did not do many examples with that, but today we're going to put everything together. Let's start with the following. A simple application right here. Find the future value if payments of 1200. I feel we might have done this question. Hang on. Payments of $1,250 made semi-annually. for 18 years. At rate at 5% compounded semi-annually. Right, so the question is, what is the future or accumulated value of these payments, right? So you can imagine yourself putting $1,250 in the bank twice a year in an interest-bearing account, giving you a 5% compounded semi-annually for 18 years. How much money you're going to have at the end of 18 years? Well, I mean, that's $2,500 a year for 18 years. So, I mean, you know, you have an idea of how much you're actually putting out of pocket. So the minimum is going to be that, right? I mean, then you tack on the interest rates. So you see what's happening there. 18 years or 36 payment periods, right? The accumulated value, $1,250 as 36 at 0.25% per period. So 1250, 1.025 to the 36 minus 1 over. Somebody work that out for us. What do we get? Right, I mean, you're paying $2,500 every year. So for 4 years, that's 10,000, and you have 4 of those. So you'll have over $45,000. What is it? 71,626 and 77. Thank you. There it is. I mean, in total, you have put of your own money 45,000, and then you have all that interest. Very nice. Consider the following question. Determine the interest rate needed to accumulate the following amount, to accumulate 120,000 over 15 years by making $500 monthly deposits. Right, so the idea is this. Suppose you want to retire and your goal is $120,000 for retirement, and you can only afford to make $500 monthly payments. What must the interest be to guarantee that you have $120,000 when you retire? All right, let's set up a let's set up an equation governing this again, right? You don't want to learn or memorize a bunch of formulas. One is enough. So let I be the annual rate compounded monthly. Right, that's what we're looking for. We don't know what that is. That's what we need to find. If you're putting in $500 every month and you wanted to accumulate to $120,000, right? We're talking about future value here. 15 years. So 12 months. That's 120 plus 60, 180 months. 180 months at interest rate I over 12. That should accumulate to 120,000. Absolutely. So let's bring the 500 to the other side there. Take out 2 zeros. So S180, what is that? 1 plus I over 12 to the 180 minus 1 over I over 12. That should be equal to 120,000 divided by 500. Then you cancel 2 zeros, and if you multiply by 2 over 2 is 1. Then you can cancel another 0. So that is 240. And now you see the issue. You see the issue, right? You cannot solve for I here. So the only thing we can do is plug in and try to get I as accurate as possible. So, let's start with something. We don't know what it is, so try. What are we really doing here? You're putting in $1 amounts 180 times, and it's accumulating to 240. So the interest rate is very small, I think. So let's try something. Try I equals 0.02 and plug it in. Plug it in, see what happens. What happens if I is 0.02? What is the left-hand side? Somebody want to work that out for us? $209.71. Mark is suggesting to use logs, and that would be fine. But the problem is, if you use log, if you take log on both sides, you're still going to have ln of I over 12. right? And you bring down the power, well, I mean, you actually don't, because you have ln of the top minus ln of the bottom, and there's nothing you can do with that anymore. That's it. And, you know, I mean, the point is you have two logs involving i's, and there's nothing to do there. And Oliver, to answer your question, Danny just answered it. It's really 120,000 divided by 500. So what? So you see, starting out with the 2%, we've got 209.71, slightly less than what we want. So our answer is going to be a bit bigger than 2%. Let's try 0.025. Let's see how that works out. In that case, the left-hand side. Somebody work that out for us. To 1812. All right, that's not going up very fast. So if we do two more nines, that brings us about to 3.5, and that's not even there yet. So let's try 0.038. Oh, I better try with 0.037. What did you get? $240, $147. So 240.15, very close, right? Just ever so slightly too large. Very nice. So it's going to be slightly less than 3.7. So slightly less than 3.7% compounded monthly. Yeah, you know, that's going to be close enough here, 15 cents. So it's just ever so slightly less than 3.7%. So, you know, I mean, a reasonable interest rate needed to accumulate 120,000. Very good. Consider the following scenario. Number 58. How did we know that we have to start with 0.02? We did not. We did not. What I suggested was you're really making 180 payments, right? In this case, you're making 180 payments of $1, and you're hoping that it accumulates to 240. You're already not far off, right? You're starting with 180 and you want to get to 240, and you have 15 years of payments to do that. So all I was suggesting is that the interest rate is probably pretty low. The interest rate is pretty small. So we started with something small, 2%. Whatever you start with, it doesn't matter. Probably it's not going to be the right answer, and you're going to have to adjust. So you start with something. If you start out with 10%, you start off with 10%, it doesn't matter. You start off with an educated guess. Well, if that was a question, then yes. Yeah. You start off with a net, because there's no solving here. You cannot solve precisely for the interest rate. So you start off with an educated guess and you adjust. If the value you plug in, if this value gives you something larger than 240, you know that you have to come down. The interest rate will be lower. If you get an answer that is less than 240, as we did here, then you know you have to increase the rate. And you keep doing so until you get to an accuracy that you're comfortable with, or that the question asks, right? I mean, the question could have asked for an accuracy to within the first two digits should have been accurate, maybe, or something. Yep. Exactly. 58. Michelle wants to have $20,000 as a down payment when she buys a new car in 6 years. So Michelle wants $20,000 in 6 years to buy a new car. How much money must she deposit at the end of each quarter in an account, paying 3.2% compounded quarterly? So that she will have the down payment she desires. So how much money must she deposit every quarter? So a likely scenario, right? You want to buy a house or you want to buy a car in 6 years, whatever the case may be, you want $20,000. How much must you contribute every quarter so that you end up with that? Right? So again, future value, right? Let P be the payment. Let P be the quarterly payment. $6 years or 24 quarters at rate 0.032 divided by 4 per quarter, thank you, A, this should accumulate to what you want, namely the 20,000. Right, again, it's always just the one formula, write down the scenario that's occurring and then solve for the unknown. No need to complicate things. This, what is that? This is 1 plus 32 divided by 4 is 8. So that is 1.008 to the 24 minus 1 over 0.008. Somebody work that out for us? $7.59 and 21. Thank you. So there you go. $7.59.21 every quarter for 6 years at 3.2% compounded quarterly. This will give you an accumulated value of 20,000. Let me point out, right, the difference between present value and future value. Right, I mean, I know I've done it before, but I mean, first of all, these relate to the same annuity, right? This is the present value of $1 payments. You're making $1 payments at the end of each payment period for n payment periods. This is what these are worth. AN is what these are worth at time 0. It's the present value of these future payments. SN is what these are worth at time N. Right, so it's the same annuity, it's the same payments, but it's worth this much right now, and it's worth this much at the end. If you put this amount of money in the bank right now, and you brought it up to time N, that should be equal to SN. Why is N 24 here? You had 6 years, and you have 4 quarters every year, right? So 6 times 4, 24. 24 quarters in 6 years. So you have this nice verbal interpretation of what's going on. Right? This annuity is worth this much at time 0, and it's worth this much at time N. If you brought this amount forward for N periods, you would get SN. Now, geometrically, I mean, it's very clear, right? Because this is just that. So 1 minus 1 over 1 plus I to the N. Over I, if you multiply that by 1 plus I to the N, these and these cancel out, And so you get 1 plus I to the n minus 1 over I, which is exactly your Sn. But the nice way of viewing it is important. Consider the following. In 3 years, Christine must pay a pledge of $7,500 to her college's building fund. What lump sum can she deposit today at 5% compounded semi-annually so that she will have enough to pay the pledge? All right, so you see what's happening? You have this payment that must be paid 3 years from now. You need to pay $7,500 3 years from now. How much must you set aside today so that you have enough in 3 years? Well, let X be the amount that you need to set aside. If you bring it up 3 years down the line at 5.5% compounded semi-annually for 3 years or 6 periods, this should accumulate to $7,500. So it's really the present value of $7,500, right? Somebody work that out for us. How much is $7,500 worth right now at 5.5% compounded semi-annually? Thank you. 63, 73, and 39. If you place that amount in the bank right now at 5.5% compounded semi-annually, in 3 years you will have $7,500. There it is. consider this. Pension experts recommend that you should start drawing at least 40% of your full pension as early as possible. Suppose you have built up a pension of $1,200 annual payments by working 10 years for a company. So you will be making $1,200 a year as a pension. When you leave to accept a better job, the company gives you the option of collecting half of the full pension when you reach 55, or the full pension at 65. Everybody with us here? Assuming an interest rate of 8% compounded annually, by age 75, how much will each plan produce? Which plan would produce the larger amount? There you have it, right? Everybody understood the issue. You have a pension which pays you $12,000 a year. You have two scenarios. Either you accept $6,000 a year, starting at age 55, or you wait until 65, in which case you can collect the whole $12,000 a year. And you know, the government kind of does that. It's not that much, but it's almost that much. I think it's 4%. It's 4% less every year. You can start taking your pension at 60. At 65, you get the full pension, and it's 4% less every year that you start before 60, going down all the way to before 65. 4% less every year for every year less than 65 to a maximum of 60. But if you'd gone down to 55, they used to offer that would have brought, you would have lost 40%. So not half, this would have been 60% instead of 50. But it's almost the same thing. So here's the question, which is better? Do you want to take a half pension starting at 55, or do you want the full pension starting at 65? So as Annie suggests, let's calculate the future value, the accumulated value. Suppose that you took the $6,000 a year and you left it in the bank. You had other money that you could live off of. You left it in the bank. You take that $6,000 every year and you put it in the bank until you reach 75. Or you start taking the full $12,000 a year at 65. and put that in the bank. Which one is larger? So what do we have? 6,000 every year for 20 years at interest rate 0.08. That's how much you're going to have if you took the first option versus the 12,000 a year for 10 years at that same interest rate. So what is this? So it's this versus this. Now, of course, without doing too much work, if you're planning on living forever, you're going to want to take the 100%. But, there's always that life expectancy business. Who knows if you're going to make it up to 75? So, right? If you passed away at 63, this would not have given you anything. Versus here, you would have had 8 years of $6,000 payments. What does that give us here? Is somebody working these out? Thank you. 274, 571, and 18 versus versus 173, 838, and 75. Thank you. There you go, right? There's almost $100,000 difference. Isn't that crazy? Yeah. So even though you're just taking half, if the interest rate is high enough, of course that plays a large role here. But if the interest rate is high enough, you see what's happening. So you want to hop on that pension ASAP. Questions? Consider this. When the Lee family bought their home, they borrowed $315,000. So this is number 76. They borrowed $315,700 at 7.5%. Compounded annually. For 25 years. They made 300 monthly payments. How much interest did they pay? I guess it's 300 equal monthly payments. How much interest did they pay? Questions? How are we doing here? What's the first thing to notice? First thing to notice is that we have an interest rate compounded annually, whereas we are making monthly payments. As such, these are incompatible. What are we going to do? We're going to find the equivalent. Not so much, right? Because if you just divide by 12, this would have been the annual, that would have been the 7.5% compounded monthly. So it's not as easy as dividing by 12, but rather what we're going to do is find the equivalent rate compounded monthly. Right? If you put $1 in the bank at rate at some rate I compounded monthly for a year, that should give you the same amount as if you put that $1 in at rate 7.5% compounded annually. So I is easily seen to be, what is it easily seen to be? 1.5 to the 1 over 12 minus 1. Somebody work that out for us. Without doing any work, it's clear that it should be just ever so slightly less than 7.5, right? Somebody's going to tell us. That low, really? I was not expecting it to be that small. It's possible that I expected something wrong, but I'm just expecting it to be slightly less than 7%, 7.5. $7,254. 7,254. Very well. I'll believe it. Thank you. Thank you. Okay. So there you go. So you see 7.5% compounded annually is equivalent, right? I mean, it's the effective rate corresponding to 7.254% compounded monthly. So that's what we're going to use. And what do we want? We want to calculate, first of all, the payments that must be made. If you're borrowing $315,700 at this rate, compounded monthly for 25 years, what are the payments going to be? You're making payments of P. Here, this is present value, right? Because you're borrowing the money right now. You're borrowing $315,700 right now for 30 months. 300 months at interest rate 0.7254 divided by 12 every payment period. This is to borrow $315,700. So absolutely, present value. And somebody work that out for us. What do we have as payments? $22.76. Then 42 cents. Thank you. We were given, so Javier wants to know how we got the interest. We were given 7.5% compounded annually. But if you're making monthly payments, these are incompatible, right? You have an interest rate compounded annually versus what you really want is an interest rate compounded monthly. So we have to find the equivalent rate compounded monthly. If you place $1 in the bank at interest rate I, compounded monthly for a year, this is what you're going to get. If you place $1 in the bank at interest rate 7.5%, compounded annually for a year, this is what you're going to get. So we equated the two and solved for I. This will give us an annual rate compounded monthly, which is equivalent to 7.5% compounded annually. It's the idea of effective rate, but in reverse. Here, 7.5% is the effective rate. So we're actually solving for the other one. We still have not answered the question yet. How much interest did they pay? They are paying $2276.42. Why is it present value? You're borrowing the money right now. You're buying the house right now. You need $315,700 right now. So you're getting that money right now. You're paying it off with equal payments. But since you're borrowing that money right now, those payments must be worth this right now, present value. So as Annie suggests, we are paying $2276.42 300 times minus the $315,700 that you actually borrowed. The rest is just interest. What is it, Annie? I suspect you've already worked that out. And you know, it's always a question of time. When are you? When are you? That's the question. When are you? Here we're borrowing right now, $376. $226. Right? More, you paid more interest than you actually borrowed. So again, you know, we're just playing around with these present value versus accumulated value, and the real question is when. When you're borrowing money for a house, you need it now. Present value. In other questions, you were saving up to buy a car in 6 years. In 6 years, that'll be the future value. Consider this. Very interesting question. In the spring of 2014, some dealers offered a cash back allowance of $4,000. So $4,000 cash back, or 0% financing. For 72 months. On a Chevrolet Silverado. So, a few questions here. Determine the payments on a Chevrolet Silverado. The buyer chooses 0% financing and needs to finance $30,000 for 72 months. Determine the payments on a same thing. If the buyer chooses the $4,000 cash back and is able to get a car loan at 3.18%, compounded monthly, for 48 months. And then obviously, which is the better deal and why? Would questions be clear as to whether we should be using future or present value in the wording? Well, here's the thing. I'm going to argue that it's clear to me. It might not be clear to you. And that's the problem. Right? I have a lot of experience with these things, so it's usually immediate to me what we should be using, but I'm quite certain it is not to you. So again, the idea is lots and lots of exercises until it becomes clear. Present or future and I'm stressing the fact that you have to ask yourself, because I know that it's confusing for students in the beginning, the difference between present and accumulated value. That's why I keep saying you have to ask yourself when. The question is when. All right. Consider this idea here that, you have a $30,000 truck that you can either finance at 0% for 72 months or take a $4,000 cash reduction and, get some financing elsewhere or pay cash, whatever you want to do. So here, if you're financing $30,000 at 0% for 72 months, I think it's crystal clear what the payments are. What are the payments? For A, the payments are $30,000 divided by 72. And there's no interest here. 0% interest. For 16, 67. Thank you. Now, what if you took the $4,000 cash back? So you were only financing $26,000. And you were only financing it for 48 months. Right? So here, 72 months, right? 6 years versus 4 years. You'll be paying the truck off 2 years earlier, and you're still paying some interest. How much are the payments here? Well, first question is, many questions. There are many questions. What are we going to use here? How are we going to work that out? Right, you'll be making 48 monthly payments, so it is an annuity. And present value or future value? When are you getting the truck? Are you getting the truck now, or are you getting the truck later on? And by that I mean, are you putting money in the bank in order to buy a truck at some time in the future? Of course, you're not. You will start paying when you buy the truck, which is right now. So what are the payments? Some payments of P we don't know. Present value, right? Because you're getting the truck right now. Present value, 48 months at 0.0318 divided by 12, rate every month. And that should be equal to 26,000. So the payment is 48 months. Somebody work that out for us. I am assuming somebody's working that out, right? Is somebody working that out? Thank you. 577 and 56. All right. Well, I mean, here, as you may realize, I don't do these questions ahead of time, so I didn't know how these would relate. So perhaps that's not such a good idea, right? Because first of all, this is 48 months versus 72. So you're not comparing apples with apples here, but the question certainly arises, which one is best for you? Should you take the $4,000 cash back or the 0% financing for 72 months? I'm not sure why they made us work it out for 48 here, but let's assume that if we had it (3.18%) for 72 months, what then? Would $4,000 cash back be better than the 0% financing, or vice versa? right? So instead of 48, let's make it 72. In this case, the payments would have been if we calculated for 72 instead, supposing we could find that loan for 72 months instead. In the earlier question, when we changed the interest rate, why didn't we change it in this question? In this question, we had the 3.18% compounded monthly. It was already exactly what we wanted. In the previous question, it wasn't compounded monthly. It was compounded annually. We had to change it to a compounded monthly rate. So in order to figure out which one we should adopt, thank you, 397 and 13, and you see what happens, right? If you're able to get a fairly low interest rate loan, it's better to take the $4,000 cash back than the 0% annual rate. Right? In the 0% annual rate, you're paying $416 and 67. Even if you are paying some interest, it's still beneficial to do so. Because the 4,000 more than offsets the interest. How are we doing? Questions? Questions on interest rates? All right, maybe a good place to end then. Thank you all for coming, folks. Good luck on your midterm. And you guys have a good break. We'll meet up again the week after next. You guys have a good one, and I'll see you then.